Yes.
I don't have.
Yeah, the lab you don't do it.
And then I just have a question. Did you count off the three?
No, usually I do count out for units, but I didn't count out for this one.
Okay.
Okay, thank you. Any more labs to turn in? So today, 4.3, we'll finish up 4.3. Tomorrow will be 4.4. And then we will do the chat for review questions for 2 days. For the test on Friday. Can somebody close those blinds back there when you get a chance to see previously? Thank you. Okay. So we talked about isotopes last week, about how you can have the same element but different weights. That's what an isotope is. So a banana, for example, has potassium in it. Most of potassium is going to be 90, or it's going to be potassium 39, which you can see up here. 93.26% potassium 39. The 39 represents the weight of that atom. 6.73% will be potassium 41. 0.01% will be potassium 40. And you can see the chart, it tells you how they're different. Potassium 39 has 19 protons, 20 neutrons, 19 electrons. And so 19 plus 20 gives you 39. Protons plus neutrons gives you the atomic mass of 39. For all of them, you can see that the number of protons is the same. Protons gives you the identity of the atom. All that changes is the neutrons. So in an atom that's not charged, number of protons equals the number of electrons. What can vary though within one kind of atom would be the number of neutrons. Since you can see potassium 40, it's 19 protons and 21 neutrons. Potassium 41, 19 protons and 22 neutrons. So they're all potassium, they all have 19 protons, but they have different amounts of neutrons, which they have different amounts of weights. So they can behave a little bit different chemically, not much, so they're usually very similar to each other. Now, why do we have very much potassium 41 and 40? That's because they're not very stable. So generally you have a stable isotope and the other ones are not as stable. And so usually you have one that's very common, the other ones are not nearly as common in the sample. Yes.
Are protons always going to be the same?
Yeah, within one kind of element, yes. So if you change the number of protons, it's a different element altogether. So potassium 19, if you were to get rid of one proton, it would now become argon with 18 protons.
Is this still section 3, by the way?
Yes, we're in 4.3. So we have 4.3 to get through today still, and then we'll go into 4.4 tomorrow. We'll have the test on Friday this week. Everybody have these down? So atomic mass unit, we talked about this. It's how we measure the mass of atoms. It's the unit to measure mass for an atom. Scientists arrived at this unit by taking a carbon atom, carbon 12 atom, and dividing that by 12 to get the mass of one atomic unit. So atomic mass unit is defined as 1/12 the mass of a carbon 12 atom. Usually you will see AMU as the abbreviation. You might just see it as U for the abbreviation of the unit. So AMU or U for the abbreviation. It's how we measure the mass of very small things like protons, neutrons, and atoms. And then a neutron and a proton are both roughly one atomic mass unit. You can see the chart. A proton weighs 1.007276 atomic mass units. Neutron weighs 1.008665 atomic mass units. So you can round those both to 1. And they're pretty much one atomic mass unit for both. Now, neutrons do weigh a little bit more than protons, but not by much. And you can see that an electron is much, much smaller than both. And that's why we can disregard the mass of an electron in atomic weight, because we can see the electron is 0.00005 atomic mass units. So compared to one, that's almost nothing.
Wait, so for one, does it mean that the AMU equals nearly the mass of a proton?
Yeah, well, that's right. So one proton is about one AMU.
You want us to copy that too?
The chart, you don't have to, that's in your book too, if you refer to it on page 119. You don't need to copy that down. Just know in general that a proton and neutron are both about one atomic mass unit, but a neutron weighs a little bit more than a proton. That would be important to know too. And an electron weighs almost nothing compared to the electron and the proton. Can I have these down? The chart, you don't have to worry about copying that down. Atomic mass is the weighted average mass of the isotopes of the element. So every element has isotopes. And so that's why in the periodic table, you won't see any atom's mass as a whole number. They're always going to be decimal points because they're always the mass, average mass of at least two or more isotopes. So a single atom would have a mass that's not a decimal number. But if you have different kinds of isotopes and you average them together, you will always get a decimal number for that average mass. Everybody have that down? So to get the average mass of isotopes, we did this with a Chex Mix on Friday. You take the mass of that one particular atom. You know, in this case, we're looking at this one right here. Its mass is 34.969 AMUs. Percent abundance, 75.78%. You get the mass contribution. You multiply the mass of the atom by its percent abundance. Same thing with the other one. Mass times percent abundance. You add these two together, 26.5 plus 8.953. That gets you the average mass of the sample. So to get an average mass, we can't just add up the masses divided by 2. We have to, because for this one, we have 75.78%, that's chlorine 35, and only 24.2% is chlorine 37. So we have to take that into account and multiply the mass by the weight, or by the percentage, to get the average mass of that sample.
So what's the formula for average mass?
Average mass, you get the mass contribution by multiplying the percent times the weight. Then you add up each mass contribution to get the average. So you start by taking the mass of the one individual atom and multiply it by its percent abundance.
Okay.
Now, with the percent, though, I didn't show it on here, That's gonna be 75 over 100. You do the percent divided by 100. But then you get the mass contribution right there. Do the same thing for other atoms too, and add up each of their mass contributions to get the average. It's like what you did on Friday in the lab. It's the same exact procedure. Does that make sense to everybody? How you do that? Don't worry about that. Okay, so that's it for this section, 4.3. We'll do the rest tomorrow for 4.4. So on page 121, I want you to work on 18 through 24. I'm gonna set up a short demonstration for you all while you're doing that. After you finish with the homework, I'll do the demonstration. So on page 121, do 18 through 24 for right now.